you remember why I put it up on the board, what I was trying to impress upon you with this picture? Well, that's the problem. You may remember that I put things and they look familiar, but none of it sunk in. So let's talk a little bit about this car traveling on the road, because that's what this is. We're looking top down on the car as it travels along the road, and the car is making a right turn, then going straight, making a left turn, and continuing on the roadway. Do you remember that when I talked about this, the reason I talked about it was to impress upon you that if you're trying to change direction, there has to be something that pushes you in the direction of the turn. So although all these blue arrows might represent the speed of the car and even the velocity because they have a direction, when the car is traveling here, there has to be a force this way that causes the car to turn. Here, that force is unnecessary because the car is traveling in a straight line. But here, there's probably got to be a force this way to cause the car to turn. Remember, the car could be speeding up and slowing down at the same time as it's trying to make the turn, but there has to be a component of a force in the direction of the turn. And that was our introduction to the idea that there are forces that can be used to change the speed of the car. We call that a tangential acceleration, because that would be an acceleration that would be this way or this way. It'd be tangent to the curve. But there's also forces that can be used to change the direction of the car. We call that a centripetal acceleration, one that's curved. You can do both at the same time. That means that if my car here, say, is speeding up at the same time that's making a left, the net force would have to be this way. So there would be a component to cause the car to increase its speed and a component to cause the car to change its direction. And these were things we talked about. It was about, a couple weeks ago. I'm going to add to that today and talk about different ways that we're going to use this as part of our conversation now. How do we calculate centripetal accelerations, and how do we use that to calculate net force? I want to start this conversation out with kind of a statement of, it's not what you're going to read in your physics book. I'll say it like that. But I want you to understand that there isn't a centripetal force. I might even say, well, what was a centripetal force? But I don't mean it. There isn't a centripetal force. There are forces that cause centripetal acceleration. How often do I write out a definition? Is it often? No. I want to be very clear. We are not adding a force to your list of forces. You're going to make this mistake in a few minutes, but I'm telling you right now, there isn't a force that we call the centripetal force that causes things to turn. There are a collection of forces that we have learned to put in the summation portion. Things like tension, normal force, friction, gravity. One of those, or a combination of those, can cause an object to change direction. But there's no special force here. There has to be an unbalanced force from your list that you already know that, because it's unbalanced, causes your object to change direction. So let's pick an example here. Imagine I have a car and it's approaching a dip in the road. So it's got some velocity. Now, if I tell you that the car's got the cruise control set, so it's traveling at the same speed all the time, say 10 meters per second. When it makes it to here, is it traveling in a circular path? I mean, it is, right? The roadway, because it dips, is a circular path. I know you think I'm only talking about when things go left or go right, but that doesn't have to be. It'll be at Busch Gardens on Friday. Lots of your rides are going to go in curved paths, and some of those are curves on the bottom and curves over the top, right? So a curved path is any time the object changes direction, and this is a change in direction. If the car is going this way, do you think the car is going to burrow into the ground? I would hope not. I think in this circumstance, the car is going to be tipped upwards to make it out of this ravine. The ravine itself probably has a radius of curvature, something that would describe how curved the roadway is. Now, if the car is traveling at a constant speed, 10 meters per second, what forces must be acting on the car at this moment? You have a list. Start at the top.
Normal force and gravity.
It's going to have to be gravity, sure. In fact, this would be the same gravity that was acting on the car over here. Is that going to be any different before I enter this ravine than after I enter the ravine? Does the weight of the car change while you're driving it? No, not much, not likely. I mean, you're burning gas, but not likely. And yeah, it's touching the ground. So here, I would expect the normal force to be equal to the weight. But if there's no other forces acting on the car, I'm going to have to expect the normal force here to be greater than the weight. There has to be an unbalanced force that acts on the car for the car to travel in a circular path. It's the only way the car can travel in a circular path is for the forces to be unbalanced. And there's no special force called a centripetal force. This is why if you are driving in your car and your car goes through a dip, you feel like you're being pushed into the seat. That's the normal force pushing upwards more on the car for that instant to cause the car's direction to change. The normal force increases under this circumstance. If you're asked to do this problem, and you will be, the first thing I would recommend you do is make the direction towards the center of the circle your positive direction. That's the very first thing I would do. It'll make these problems easier. That is the direction of the acceleration. The acceleration has to be towards the center of the circle. If this doesn't happen, the car goes in a straight line, and that straight line is right into the road. So there has to be an unbalanced force. In this case, normal minus weight will have to equal MAC. And this part, well, that all depends. How fast is the car going, and what is the radius of curvature of the dip? So, roller coasters play with this a lot. They try to change the normal force acting on you. When the normal force acting on you increases, you feel heavier. And when the normal force acting on you decreases, you feel lighter. Because you don't feel weight, you feel the response of the ground and the chair to your weight. So manipulating normal force is a regular way for a theme park to try and thrill you. So this, the bottom portion of every single roller coaster, you go down and you kind of flip around that hill, all of you feel more pressed into your chair. That's on purpose. And this is the force they're manipulating. They're manipulating the normal force here. In fact, if you look carefully at it, they can kind of determine how much they want you to feel. If you're not moving at all, this term is 0. As you move, they can manipulate that term to make the normal force greater and greater and greater. At some point, if you're riding, say, let's go with Montu. How many of you have ridden Montu before? Montu pulls 4 Gs 7 times. So when I say that a ride pulls 4 Gs, it means it makes you feel an acceleration 4 times that of gravity. That means it's trying to make your normal force 4 times your weight. So that makes this the biggest part of this. You're going that fast through that tight of turn. Now, Montu does it a number of different ways. Lots of left and right zigzag turns, lots of bottoming out after you do a corkscrew turn. And that's how they ramp this up. But you weren't probably around long enough to ride the old version of Gwazi. Anybody ride the old version before they decided not to let people on it anymore? Because Gwazi was boy, was that a rough ride, wasn't it? Almost always left Gwazi with a headache. Now, I've not ridden Iron Gwazi, but the original Gwazi was a regular wooden track roller coaster designed to be like the Coney Island Cyclone. It was modeled after that wooden roller coaster that's in New Jersey. The interesting thing about it is that wooden roller coasters are designed to be rough. It's on purpose. They use steel wheels and steel tracks, and they use the wood and the noise and the weaving in and out of the track to try and elicit fear. And the roughness of the ride is intended to make you feel like things aren't working the way they're supposed to. The ride was regularly inspected every single morning. It was fine. I didn't particularly enjoy the experience of Gwazi, but it wasn't a terrible experience. The interesting thing about it is Gwazi tries to make you feel like you're being thrown out of the car. It's not accident. They do stuff like this. Same kind of car. Car approaches this hill and goes over the top. Gwazi never inverted you, right? The original Gwazi, you were never inverted. You always were on the top of the track facing upwards. Inverted coasters do something different, but this one never inverted. Now, in this particular track, or this particular instance, you understand that this would be the radius of curvature, correct? You're going over the top of the track. Your velocity is in this direction. You get that there's still only two forces acting on the car, right? There's going to be weight downwards and normal force upwards. Those forces still have to be unbalanced. In fact, it is the fact that they are unbalanced that makes this an exciting ride. But you can't change the weight while the car is in motion, which means the normal force responds to this circumstance by being less. This is on purpose. Now, if we make downwards the positive direction, we get mg minus normal force equals m v squared over r, just like before. Now, if you're driving your car and you go over a hill like this, you should be careful. This is a limiting factor problem. And I don't think you guys fully appreciate what that means, so let's kind of work this one out. And I've lost like 3 of you who've decided you're just not paying attention or not participating. I would pay attention. This is your test. I'm just explaining it to you. If you look at the right side of this, if you're driving a car, you can only adjust one of these things, correct? This is you driving the vehicle, you determine the car's speed. You guys follow me? So you can make the right side of this equation bigger or smaller by just increasing the car speed or decreasing the car speed. You really can't do much on the left side, can you? The left side is what the road is doing to the car and what the earth is doing to the car. While you're driving, is this term going to change very much? No. So you know how to make the right side bigger. Just go faster. How do you make the left side bigger? I'm subtracting something from the weight, right? So I have to make the normal force smaller. It's the only way to make the left side of the equation bigger is to subtract less from the weight. You understand there's a limit to that, right? The limit is you can just subtract 0. The normal force can't pull the car downwards. Now you understand that if the normal force goes all the way to 0, you're no longer touching the ground. But that's what happens. If you go too fast over the top of the hill, you are no longer in circular motion. You are a projectile. So if you go too fast, you jump your car. Now, roller coasters get around this, right? They put a harness on you, a safety belt on you, and they clamp onto the wheels. So they can pull downwards, pull tension instead of a normal force. So roller coasters do that. Your car, not so much. Now, I would highly recommend not jumping your car. Highly recommend it. It's not like the movies. Has anybody been in a car that has been airborne? It's fun if it's not your car. It's a lot less fun if it's your car. I lived in a small town. Jumping your car was something you could do. And I've been in cars that have been in the air. I did not enjoy, the airborne part's fine. The landing part, not so much. It tended to damage the front end of the cars. Bad. I would not encourage it. Not fun. But in this state, somebody, thinking they were being good parents, decided to make a swing for their kids. They'll just make it themselves, they said. It'll be fun, they said. They went to the hardware store and bought chain. The chain said it could hold up to 120 pounds. Great. They put their little kid on it. The kid's only 60 pounds. You understand that when your kid swings, they're going to make it to the bottom here. And there has to be an upward tension and downward weight. But the only way they travel in a circle is if the upward tension is greater than the weight. The chain can't support the weight of the child. It has to support 2 or 3 times the weight of the child. Well, if you do that wrong, you hurt your child, right? The chain snapped, the whole thing came apart. And ended up killing 2 kids. When we talk about engineering things, you can't engineer them to stay still if they're designed to move. So all of these things, when we talk about dealing with the force, there's got to be an unbalanced force. And these systems are dynamic. Go ahead.
Wait, so have the chain break if it can hold the weight?
It couldn't hold the weight. It held the weight of the child if the child wasn't moving, but it needed to be able to hold 3 or 4 times the weight of the child because the tension had to be greater than the weight of the child. Right? It needs to be unbalanced for the kid to travel in the circular path. Is going around a swing a circular path?
Yeah, but I thought the tension would be up to 180.
That's still not 3 or 4 times the weight of the child. Do the math. You do the math. You're not even taking notes, so I really don't feel like investing too much here. You do the math. Go with a 3-meter length cord. I'm giving you the numbers.
Yeah.
Have you ever been on a swing before?
Yeah.
All right, so you understand how a swing works. Some of you have operated a swing before. Excellent, excellent. How far back do you think you can pull the swing outwards? You've been on a swing, right? When you're on a swing, do you get yourself to be here? I mean, I've been on a swing. Swings are fun. There's very few rides still available in the parks. Swings are one of them. You can still ride a good solid swing today. Now, 3 meters is a relatively short swing length, but it's usually safe enough for children. But that means that you can get about 3 meters of height. Now this part, let's do some math here, but if you drop something from 3 meters, how fast is it going when it reaches the bottom? Can you do that problem? You're about to. It's a motion equation problem. And since I know who's been paying attention and who hasn't been, we'll do that problem. Delta x is going to be 3 meters. Initial velocity at the top will be 0. Final velocity at the bottom, unknown. And we are accelerating by gravity. So one of you needs to tell me how fast you're going under this circumstance. Did you use...
Yes, I did.
Well, it's probably a good chance then, because it's just this side, isn't it? 2 times 10 times 3. And this side is v squared, so v is equal to square root of 2gh. I'm kind of giving you a shortcut here, right? H is how far the object was dropped. G is 10, and the 2 is already in there. So you had the square root of 60. So I'm going to leave it the square root of 60 for a minute, and I'll show you why. 2 forces have to act on the kid at the bottom. Net force has to equal MAC. I'm going to make upwards the positive direction because that's towards the center. So that's going to be tension minus weight equals M times, and AC here is going to be V squared over R. You see how I'm going to leave it the square root of 60 since I'm just going to square it in a minute anyways? Excellent. So T equals mg plus m, let's see, this is 60 over 3. That's 20, right? The reason I'm doing this is to try and prove a point. I don't care what the number is. G is 10, right? Agreed? I just substituted 10 back in for G here, so it was 20, and I just did 2 times G instead. That all okay? See what I'm doing? I'm just putting it all in terms of G. to try and prove a point that even for a simple swing, it has to be able to hold 3 times the weight of whatever's on it. That's the point. You can't just guess at how much tension you're going to need. It can't just be more than the weight of the child. You have to build it enough to withstand what could be at least 3 times the weight of the child. Child's dressed, child grows, child has a friend with them, child's holding something in his hands while he's on the ride. Any one of those things contributes to this. You don't build these things to just withstand the minimum that could be necessary for the kid. You're going to need more. You don't guess. Engineering can't guess. I told you guys, my daughter's building a gate for an exit ride. I started this by talking about records, so I should at least make a point of record stuff here. One of your problems has a record in it. I found out in first period that you guys can't do this, but maybe this class will be better. Maybe you guys can do this. And I don't mean this mean, I thought this was something you guys would be able to do. I have 3 or 4 people in here who listen to records. How fast does a record go? Oh my word, you have records and don't know how fast they go. There are 4 speeds on most record players. Only 2 were really used relevantly in this country after the 20s. The 20s, they would use the 72 speed, but after that, generally we had long play and short play records. They were 45 or 33 and a third RPM. This is an angular speed, not a linear speed. The entire record is spinning at 33 and a third RPM. So if you're, say, a bug on the record, one of your problems in your homework, say we have 2 bugs on the record. If they're both on the record and the record's spinning at 33 and a third RPM, both bugs and the record all have the same angular speed because they're all making 33 and a third revolutions every minute. That's what RPM stands for. The term we use for a speed like this is either rotational speed or angular speed. I'll use both phrases. The symbol we use is the Greek letter omega for this. Looks like it's just a fancy W. But understand, I will refer to it as omega, the angular speed. Now, if both bugs are on the record and record spinning at 33 and a third RPM, which bug has a faster linear speed? Bug A or bug B? B, sure. It's going around in a bigger circle every rotation. If this bug is 10 centimeters away and this bug is 25 centimeters from the center, can you tell me what that linear speed is? Do you have enough skills to do so? My first period was not skilled enough. I do want you to understand that you will have to do a couple of things here to be successful. There's many ways to solve this problem. I will tell you that there is a conversion that can convert angular speeds to linear speeds, and that's purely based on the angular speed and the radius. Just like you said, the bug further away is making bigger circles. The problem is that you can only use this when this is in radians. And I kind of found out in my other class that you guys are not proficient in dealing with radians. Are you guys proficient at dealing with radians? I'll give you a hint. There are 2 pi radians in every 1 rotation. You're supposed to know this. Again, information you've been taught that seems like it's gone away. So 2 pi radians for every 1 rotation. Can you use this to figure out my answer? My sense is that you guys need a method, and I'm afraid you guys don't have a method. I'm going to show you a method. I want you to learn how to convert this to radians per second. And I have a plan for this. So if you have a method, use your method. If you don't, use my method. You ready for my method? I'm a unit multiplier kind of person. So I'll start with 33 1/3 rotations per minute. Start by writing your thing out as a fraction. Then use unit multipliers. A unit multiplier changes a unit, but is essentially multiplying by 1. For example, pick what we're going to change first, the rotations or the minutes. Rotations? All right, so rotations are on the top. If I want to get rid of rotations and change to radians, I need to put on the bottom the thing I'm canceling, because the thing I'm canceling is on the top of the original number. Now, if you're just writing down what I'm writing down, you'll never figure this out. Write down what you have to do, not what I'm doing. So if you're canceling out something that's on the top, you put the thing they're trying to cancel on the bottom. If you're canceling out something that's on the bottom, you put that thing on the top. Now, you'll have a leftover side. You put what you're converting to in the leftover side, radians. Now, you'll need a conversion fact. So 1 rotation every 2 pi radians. Now, you can string these together and convert more than one thing at a time. Minutes on the bottom, I'm going to put minute on the top. Second on the bottom, again, your conversion fact. Be good at this by tomorrow, please.